afternoon, everyone. My name is Levin. I'm a PhD student at Columbia University, and I'll be presenting, enabling integrated circuit-based full duplex wireless in GNU Radio. So this talk comes about as essentially a summary of the FlexICon project at Columbia, which is a research effort into enabling full duplex wireless networks from the IC level all the way up to the network algorithms and further. So when we say full duplex wireless, what we mean is the simultaneous transmission and reception on the same frequency at the same exact time. So normally you look at any other device, your laptops, your Bluetooth headphones, whatnot, they're operating half duplex mode. And the reason for that is that you don't want your transmissions to end up leaking back into your receiver, right? The relative power level is between 70 to 110 dB between your self-interference and whatever you're trying to pick up from the other node. So well, for a long time it's been seen as an infeasible problem to combine those functions, transmitting and receiving on the same channel. So the reasoning why we'd want to do that in the first place is a problem of resource efficiency, right? You have a lot of wireless devices right now in the network. Everything is trying to compete for the same resources. If you're able to remove the need to split up your transmit and receive streams on different resources, you're essentially doubling the amount of resources you have. To get over that, to enable that, you have to get over that self-interference problem. So what we do is you really just throw the whole toolbox at it, right? Spoke about this already. Essentially, what we do is you have sort of essentially 3 levels of self-interference cancellation that you could apply in your typical full duplex transceiver. First, you have your passive RF isolation, which is your antenna interface, whether you have a single antenna scheme, such as a circulator or an EBD, or you have a dual antenna scheme where you literally use the physical distance between the two for your isolation. That serves as the first step. Next step is your RF or RF analog cancellation. The reason you need that is because you don't want to saturate your receiver, right? If you saturate your receiver, you can forget any hope of picking up anything else besides your own self-interference. So once we reduce that down to the point where you're no longer dealing with those desensitization issues, finally you can clean everything up with digital algorithms already on the compute side of the node. So at FlexICon, we were investigating 3 different RF canceller classes, right? And this is just a quick overview of our history. First, there's the very simple phase and amplitude-based equalization, where you take a copy of your transmitted signal, you you play with the amplitude and your phase settings so that you have perfect destructive interference, hopefully, and just feed that back into your receiver where, again, hopefully you destructively interfere with your self-interference. Next step was to explore frequency domain equalizations, where essentially you have banks of passband filters, which again, you can play with a bunch of different configurable settings there. And finally, time domain equalization, which applies the same principle as before with the phase and amplitude-based equalization, except instead of explicitly modulating the phase, modifying the phase, you are trying to emulate the delays that the self-interference travels through. And essentially, again, your goal is to have as much destructive interference as possible. So we took these concepts and, well, our collaborators developed 3 ICs that do just that. I'm not going to go into how they developed these ICs. I'm going to leave that to the RF engineers and their magic, or I guess the RFIC engineers and their magic. But we developed these 3 ICs. Now the question is, fantastic. We have some sort of semblance of a RF full duplex front end. How do we build a whole full duplex radio around that? So we have 3 classes of ICs, therefore we have 3 classes of radios. The very first one, the first generation, uses that phase and amplitude-based canceller. It's very simple. The front end has only a single tap with 2 configurable parameters, your attenuation and your phase. You can configure it through GNU Radio, through Python, through whatever other means you want, using Ethernet to SPI interface. And what you get is about 42 dB of RF cancellation across a 5 megahertz bandwidth, with the rest being cleaned up by digital SIC, which again we're going to cover later. The next generation sort of took that to the next step and added the passband filter banks to that concept. So now you have a lot more parameters you can play with, right? You have the center frequencies you can play with, the quality factor of your filters, and now it added the capacity to essentially have 2 passband filters in parallel. So now we have 2 taps instead of 1, which gives you greater flexibility in your cancellation. And that now enables you to have up to 20 megahertz of bandwidth that you can realistically get good cancellation, and therefore enable full duplex communication through. And now the next step, the current work in progress, is the 3rd generation full duplex radio, which is a time domain canceller, which consists of essentially 16 parallel RF taps, each with variable gain and variable delay. And whereas the previous 2 generations of front ends had relatively small configuration parameter space, right? It's something that you could fiddle with by hand in GNU Radio and find the optimal cancellation. Here you have a parameter space on the order of 10 to the 19th. So at this point, you need to start investigating configuration algorithms. How do we take what self-interference we measure and apply that so that we can find the optimal configuration to cancel that out as much as possible? And so here's the next question, right? This is the guts, right? How do we actually, fantastic. We have the front ends, we have our radios. How do we actually control this? How do we find how to configure them and such? Well, the answer's in the corner, right? We use GNU Radio. So the next sort of set of slides, I'm just going to go through the key processes that we developed throughout the years of the FlexICon project and go over the sort of design considerations you need when implementing full duplex. So first things first, we have to consider there's the self-interference aspect. We still need to be able to sense that self-interference and make sure that we can still separate out the received packets from your own transmitted stream, right? So in order to do that, we essentially created an encapsulation system where we're agnostic to whatever standards you use, whether it's 802.11, whether the GR 802.11 block or 5G standards and such. We prepend to that a couple of pilot slots, 1 per dedicated device. In other words, even though your payloads are still synchronous in time, there's still a little bit of that quiet zone so that you can sense your own self-interference, and each device can do that. Well, fantastic. So we have those in place. The next question is, how do we make sure that, A, we know where our self-interference is, and B, how do we know that we can be aligned with the other node? So this is where our synchronization steps on the receive side come in. So, first of all, you need to have intranode synchronization. You need to be able to know that when your self-interference comes in, you can detect it, you can separate out your pilot slots, your payload. And if you want to have successful digital cancellation, you obviously need to know what you're transmitting. That is where all this synchronization comes in. You want to make sure that you have a good estimate of your self-interference channel. So essentially, I'm not going to go through the algorithms right now in the interest of time, but through a series of coarse and then fine-tuning, you can line up your self-interference stream with your transmitted stream and get essentially enable the next steps in the process. Bless you. Next, we add the next stage where you have 2 different nodes. You got to, as we said, they need to have their payloads overlap, otherwise it's not really full duplex, right? So similar idea, you have 1 node transmit out a initial packet, and the other node would synchronize to that. So that now you have each node knowing exactly which slot it's supposed to, which pilot slot belongs to itself, and the actual data is overlapping in time. Fantastic. We have those pilot slots. What are they actually used for? So as I said, because that is a quiet period when the node knows that the only thing transmitting during that time is itself, we can essentially recover the self-interference channel from that. And so there are different ways of going about doing this. What we ended up implementing was a simple least squares estimator. And that gives you a good idea for the, that can be used in 2 different ways. First of all, you can use it for your digital cancellation, which you should be. You need to know what channel you need to cancel out. But second of all, that can be used to then inform whatever configuration algorithms you need for the RFIC canceller optimization loop. Again, with digital SIC, there are many different ways in literature how to approach this. What we ended up doing was we essentially used the truncated Volterra series model to model the self-interference channel. So what that gives you is it's essentially multiple order filter that you use, you develop that filter based on your channel estimation, then you apply it to whatever signal you transmitted and subtract that off from your received signal, and hopefully what you should end up with is just the received signal from the other guy. We found that very often using just a third order model is sufficient, and even then, the first order model, as shown at the bottom, is enough to get you a good chunk of the way. Now, to sort of keep track of all these different processes and everything at once, you sometimes have UHD errors, you sometimes have additional peripherals that are connected. What we ended up developing was, for each generation of radio, there's one primary controller, which doesn't do any data processing of its own. It essentially just orchestrates between all those different sub-processes using GNU Radio's very handy messaging system. And what you could do then is, whatever is going on in your flow graph, whatever data you're getting from your flow graph, can then be transmitted and used further down the line in those peripherals. So for example, the first and second generation radios are configured over SPI using that SPI interface over there on the left. Right? For the third generation radio, where the configuration algorithm is heavier, and that's offloaded onto an FPGA, the controller block provides the mechanism to transmit that channel estimate info to the FPGA. So that's sort of the logic and thinking that goes behind that. Is the video going to play? Yes, it will. Yes, it will. There it is. So what you're looking at here is actually what this optimization looks like, not in real time, a little bit slowed down. So at the very top is your transmitted signal power. In red is after RF cancellation. You can see that's jumping up and down, well, moving down as you're optimizing, then up again because we're restarting the loop each time, the optimization loop each time. And in green is just the noise floor, which is whatever is left after digital SIC is done. Again, this is looking at the channel estimates obtained from the pilot, which does not contain any trace of the other signal. When this is applied to the payload, you will likewise see only the received signal coming from the other node, and none of your self-interference at the end. And this is essentially a map of what, or I guess a timeline of what that cancellation looks like over time. And throughout the process, we've developed several different algorithms for controlling each of these three canceller types, RFIC canceller types. And whether the algorithm is run in GNU Radio itself or offloaded to external hardware, we can see that we can get cancellation down to the noise floor across all three generations, and that enables the actual communication step, which obviously comes next after the radio design. Now, not everybody has the hardware. We recognize that, but everyone can develop algorithms for higher layer experiments, or for example, for configuration for going from the channel estimate to the optimal configuration or digital cancellation algorithms. So what we did is we integrated these three generations of full duplex hardware into the Orbit testbed at Rutgers and the Cosmos testbed at Columbia. So over on the left, what you're looking at is a Gen 1 radio connected to a USRP N210. It's one of 100 nodes at Orbit, and that enables, for example, experimentation with hybrid links between full duplex and half duplex devices. On the right, you have also the Gen 1 radio, but set up in a mobile fashion, so that now you can take this outside, see, perform channel characterization measurements, see what happens when it's on the move. That's connected to a B210, and that's sufficient for a battery pack to power it. The second generation radios, we have 4 of them set up in Cosmos in this grid fashion. So now we can start looking at, okay, we have links, what about actual network level communications? The third generation is coming soon. As you can see, it's still in the anechoic chamber, so that should be enough of a hint that it's in the process. But the key point that we're trying to make is that this is open and available for anybody to use by just logging into the Orbit or Cosmos testbeds. It's entirely powered by GNU Radio. We have several experiments loaded already as server images. And it's open for anybody to come in and start playing with the full duplex hardware and building up those experiments and developing the standards and protocols to actually integrate full duplex further up the communication stack. And that's about that. Looks like we're at time, so I'm happy to answer any questions anyone has.